All right, welcome to Group 1's presentation for the Google driverless car. This is for CS656, Fall 2014. Purpose of this presentation is to discuss the innovations that are created from the driverless car, as well as any legal and personal implications that may result of this new technology. So first, talking about the hardware. Purpose of the hardware is to basically emulate the senses that a human has. We use our eyes with our binocular vision to assess distance. We listen to screeching brakes and sirens to avoid collisions. And likewise, the Google car has to do the same. The primary sensor is a LiDAR that's a portmanteau of light and radar, and basically uses reflected laser light to create high resolution maps. This is not a new technology. It was developed in the 1960s by organizations such as the National Oceanographic and Atmospheric Association to survey the environment for disaster planning and environmental issues. Here we can see a sample of what that would look like with mapping the environment with LiDAR from the air. So LiDAR is commercially available from Velodyne. They commercially sell LiDARs to the public. Has a 360-degree field of vision of a range of 100 meters. Although the LiDAR is impressive technology for creating a virtual map of the entire area, it's not very good for close-up objects, such as bumper-to-bumper traffic or parking. For that, we've got pairs of stereo cameras on the front and back of the car. And what that does is they're placed a short distance apart to emulate the parallax that we have with depth perception with our two eyes. And that's good for judging distance of less than 30 meters. For closer objects, less than 6 meters away, use a sonar system as available on commercially for current vehicles. For the visual recognition of traffic lights, stop signs, and pedestrians, a front-facing camera is also used. For position keeping, a commercial GPS is primarily used. However, GPS has an error of up to 30 feet, so that has to be corrected by a position estimator on the left rear wheel. That'll keep the car in the correct lane. Quite a bit of proprietary technology has been developed by Google for this project. Google developed a CPU in-house for handling the over 1 gigabyte per second throughput that's provided by the sensors. Although this technology has been retrofitted onto existing vehicles, a prototype car is being developed from the ground up with a rounder design for better sensor coverage and no steering wheel or pedals. Redundant braking and steering systems are added for peace of mind for the human. The onboard sensors differentiate objects into different types: cars, pedestrians, cyclists, and stationary, for example. After the position is determined and boundaries and speed are determined, objects are placed in these categories based on their rough boundaries, speed, and position relative to the car. Once an object has been placed into one of these types, its behavior can be estimated. Additional features such as cyclist turn gestures are also recognized. Although a busy road may appear chaotic to us, it is easy for a computer to predict actions once it has analyzed the situation. On this slide, we see a virtual map created by the Google car. Different objects are placed into different categories, and their behavior is assigned to them. The predictive model used by the driverless car has been created by over 700,000 miles of real-world driving data. A matrix-style simulation of all of California roads was created with over 4 million miles of simulated driving to test the performance. Google has patented this method for controlling a vehicle based on a route to destination. This depends on detecting external objects using sensors, classifying and detecting those objects, determining the vehicle location, and accessing data stored on a remote service for a plurality of objects. What that means is that many objects behave the same, such as pedestrians, bicyclists, and other cars. Elaborating on that last point, the vehicle communicates with local real-time data servers wirelessly. Server retrieves historical data similar to the local state and location of the vehicle. For example, different behaviors would need for driving in New York City, vice in Nebraska. Statistical models predict actions based on this location. This data gets sent back to the vehicle wirelessly as well. After the vehicle has finished the situation, it uploads what happened back to the server so the strategies can be adjusted for further trips. As you can see in this diagram, a feedback loop is created where new information is constantly being updated to the servers. What this is creating is a remapping of America from scratch. High-precision laser maps need to be made. There are 4 million miles of road in America that need to be done. So far, only 4,000 miles in California have been done. Things that need to be captured: signs, road curvature, and stoplight height. Now we're going to transition into some of the legal implications of the Google car. As you can see, it is only legal to operate the Google car in 4 states, along with the District of Columbia. In the process of developing the driverless car, hundreds of patents have been made. Some key patents are transitioning from a mixed-mode vehicle to autonomous mode, that meaning that a driver-operated vehicle switching at a set point to driverless. Traffic signal mapping and detection zone driving. This is used to identify traffic signals and how to respond to them. The final patent that is being worked on is a diagnosis tool for determining wear on vehicle components and replacement criteria. Moving from the legal side to the business side, there are quite a few financial implications of this. First off, Google bought an entire company, Waze, in order to obtain their GPS mapping technology. Other financial issues that must be addressed is, will anyone buy this vehicle? What customers need to be targeted, and how will it affect them? Will there be a change in oil demand now that people can drive more efficiently and avoid traffic? And how will this affect insurance rates? The fact that over 90% of traffic accidents are caused by driver error will cause a huge impact on the insurance community. No matter how perfect the algorithms are made in the driverless car, there's always going to be a risk on having a machine-operated vehicle versus a human's natural intuition and discretion. The fact that people will be putting their lives in the hands of a machine may be troubling. What is more troubling is the fact that criminals or terrorists can interfere with the operation of these vehicles without even being at the scene of the crime. The advantage of having an autonomous car is to make traffic more efficient. Platooning of cars will reduce the space in between a car and the car in front of it, reducing traffic jams significantly. Issues such as drunk and distracted driving will be greatly reduced, if not eliminated. Additionally, driverless vehicles will help emergency services by coordinating a path that will allow for EMS or other services to reach the scene as fast as possible. One key issue that has to be addressed by Google in the creation of the driverless car is how are they going to protect from crime or terrorism? A hacker creating a denial of service attack may be a nuisance, but imagine a hacker doing the same thing with cars, blocking traffic in a so-called spam jam, or perhaps even causing vehicles to collide and create personal injury. A driverless car is also conducive to criminal acts such as surveillance and drive-by shootings. This concludes the presentation of the Google driverless car from Group 1, CS656. I appreciate your attention.